So this section's on the sun. The sun's sort of a garden variety star. We're just going to talk about just a bunch of the sun structure and um, some facts about it, what we know about it, some of its behavior, just to sort of get an understanding of how the sun works and what it is. So here's a picture of a solar prominence. That's just this little loop that comes up from the sun. The sun. This picture gives you some idea that the sun has a very active uh, surface and interior. It looks very constant to us, but it's very violent and very active. A picture of the Earth is included for comparison. You can see in the inset here, it's got the whole picture, and you can see some hotter areas than others based on the color in the picture. So the sun is very active. Here's some sun data. You may not be able to see this stuff if you're looking on your phone, but I'll sort of talk through a bunch of these over the next couple of slides. Maybe I'll just scoot on down here to the next slide for a minute where I've written it a little bigger. So this slide that I just showed you, you can look up the data like the sun's mass, luminosity, and all these various other facts about its rotation rate, its effective temperature, all these types of things. And I'm just going to talk some of the high points here. The sun's a typical star. That's an important thing to remember. Right? It's bright in our sky because it's closer than the other stars. The sky is full of stars. The sun's somewhere in the middle in terms of size, mass, temperature, brightness, all the things you might expect from a star. Right? The sun is one astronomical unit from the Earth. That's kind of how we define an astronomical unit. Just the average distance from the Earth to the sun is an astronomical unit. And it's a little under 100 million miles, about 93 million miles. Throughout most of this stuff, we just round numbers to the nearest power of 10, just so that they're easier to sort of talk about. Having said that, the mass of the sun is about 333,000 Earth masses. I might round that to 300,000 Earth masses or something like that. So it's the Earth is minuscule by comparison to the sun. The diameter of the sun is about 870,000 miles, often rounded to a million. It's about 100. It's actually 109 Earth diameters across. And so, it's 100 Earth diameters across, 100 Earth diameters up and down, 100 Earth diameters in each of the three dimensions. And so you could fit about a million Earths inside the sun. The surface temperature of the sun is about 10,000 degrees Fahrenheit. You'll see it sometimes in Kelvin. Physicists usually use the Kelvin scale, which is about a factor of 2 smaller. In Kelvin, it's about 5,800. The temperature of the core of the sun is about 27 million degrees Fahrenheit. So that's a big difference, right? The outside, the skin of it, the surface of it, it doesn't really have a surface. The thing that you look at, the yellow ball, and we'll talk about this in a minute, the thing that we see when we look at the sun, like on the horizon, you're seeing what's called the photosphere. And that's at about 10,000 degrees Fahrenheit. But all the energy comes from inside the sun, inside the core, which is about 27 million degrees. We'll talk about that in the next chapter, not in this set of slides. The total power output of the sun is about 3.8 or 4 times 10 to the 26th watts. And so, if you ever buy light bulbs, sometimes you get a light bulb to be a 100-watt light bulb or a 150-watt light bulb or a 60-watt light bulb. Well, if you had to replace the sun with a light bulb, you'd have to go to Lowe's and buy the one that says 3.8 times 10 to the 26th watts. That's an enormous amount of power. From that, we can kind of get the solar constant, which is 1,370 approximately watts per square meter. What that number is when you're at the distance of the sun where the Earth is, that gives you a measure of how much power per square meter you're getting. And so if you put up a solar panel and collected sunlight, like you were going to power your house or something, and you were able to get every little bit of energy out of that light that's shining on your solar panel, in other words, none was reflected and none was lost due to inefficiencies or whatever, you would get 1,370 watts per square meter. And so if you had a house that needed, 20,000 watts, you'd need about, whatever that is, 10 solar panels or something like that. What would you be? More like maybe 17 solar panels or something. Of course, by the time sunlight gets through our atmosphere, a lot of that energy gets filtered out, and your your solar panel, if you have it on your roof, is never square on to the sun, so you're losing a bunch that way. You might get 300 or 400 watts per square meter, or even less than that. So you would need a whole lot of solar panels. This is becoming a more and more important topic for how to power homes. But this solar constant, this thing we call the solar constant, is what the sun is putting per square meter where the Earth is. And this number goes up and down depending on what the sun is up to. And so people who are interested in climate, for example, are really interested in the solar constant. The solar constant is affected by the sunspot cycle and is an important number for climatologists. The sun exhibits what's called differential rotation. That means its rotation, its equator rotates faster than its poles. And so that's how they first determined that the sun wasn't a solid. It's because when they could see sunspots on it, and we'll talk about sunspots in a little bit, the ones near the poles were going around slower than the ones near the equator. And it would be, if you were watching the Earth from far away, whenever North America came by, as the Earth turned, and you were watching it, say, from the moon, you would always notice that South America is right underneath it. Well, that doesn't happen on the sun because the equator is turning faster than the poles. That's also true, by the way, of the Jovian planets. They all exhibit differential rotation. They rotate at different speeds at different latitudes. The average density is about 1.4 grams per cubic centimeter. This is much more in line with the Jovian planets, right, than it is with the Earth, with the terrestrial planets. It turns out that number, though, is a little weird because the core is very dense and the outer layers are very diffuse, so there probably aren't any real regions in the sun that have this density. It's just what they average out to. So the density of the core is about 150 grams per cubic centimeter, and maybe you don't remember those numbers very well, but water is 1 gram per cubic centimeter. Iron is 8 grams per cubic centimeter. Lead is 11 grams per cubic centimeter. Gold is 19 grams per cubic centimeter. And so this is 150. The Earth's core is very, very dense. Now, we'll encounter some stuff later on that's way more dense than the sun's core, believe it or not. Sorry, the sun's core is very dense. It's 150 grams. The Earth's core is about 11 grams, so it's 13 times more dense than the Earth's core. The density of the outer layer is less, so that's the core. The density of the outer layer of the sun is less dense than the Earth's atmosphere. So the sun does this weird thing where its core is very dense, and as you get away from the core, its density is very, very low. This number is kind of only maybe interesting in certain circumstances. The sun is viewed from the Earth as about 1/2 degree in angular size. So if you were to measure the angle of the sun that the sun takes up in the sky, it's about 1/2 degree. It's a little smaller than your finger at arm's length, typically, than your fingertip at arm's length. Don't test that, but you can test it on the moon, because the moon and the sun have almost exactly the same angular size. This is Cecilia Payne-Gaposchkin. She was a British astronomer. In 1925, she did a doctoral thesis on understanding the composition of the sun and the stars. There were a lot of women in the early 1900s at Harvard who made very important discoveries that were taken by men for one reason or another. Women weren't allowed to have faculty positions, and they weren't. So they didn't get credit for a lot of the work they did. They were often she wasn't, but they were often the spouses of faculty there. So they were just smart women who were interested in this stuff and were doing it. And what Cecilia Payne did, the first thing she did that was really important, was she looked at the spectrum. We talked about spectrum in this class. She looked at the spectrum of stars, and she noticed that it was dominated by hydrogen and helium. And so she concluded that stars are made of have a huge abundance of hydrogen and helium. And so most scientists at the time were convinced that the sun was made of the same stuff as the Earth. She used spectroscopy to determine the composition of the sun and found that hydrogen and helium were the most abundant elements on the sun at the time. This is very different than what scientists believe. She was really taught, she was almost bullied out of drawing these conclusions by the men who were running the observatory at the time, or heading those scientific projects at the time. And so when her ideas were returned to, she wasn't given much credit for it, but she has been since then. She lived until 1992, so she lived long enough to, I think, feel like she got some credit for her work. So this was really important. They figured out that the sun is made of different stuff than the Earth is made of, and that was a very important discovery. So let's look at the sun a little bit. We've looked at planets. The sun has sort of three. When we talk about the Earth, we talk about the core, the mantle, and the crust. With stars, we talk about the core and a radiative zone and a convective zone. And so you can kind of sort of see them here. They're not as easily delineated maybe as the others are, but we'll talk about what they mean. By the way, you can look at other parts of the sun here. And so this is a prominence. We showed that earlier. It's just a loop that comes up, right? When you look at the sun, let's say it's on the horizon, what you're really seeing is the photosphere. That's this layer here. It's the yellow ball. It's maybe not pictured perfectly here, but just above the photosphere is the chromosphere, and it's very thin. And sometimes you'll see touches of it during a solar eclipse. It can be drawn out by photographic techniques that don't necessarily look at visible light. So we can use different kind of tricks to get it out when we're looking at it. But so this is the chromosphere. It's above the photosphere. And then the corona, when you're a little kid and you draw a picture of the sun, you draw a yellow ball, that's the photosphere. And then you draw little rays going out, that's the corona. And so the corona is the outer stuff. So there are three layers to the sun: the core, the radiative zone, and the convective zone. We'll talk about those in a little bit. And there are three layers to the atmosphere: the photosphere, the chromosphere, and the corona. And there are other little interesting things like this sunspot. We'll talk about sunspots and this prominence here. So let's just start with the three layers of the sun. The core is where fusion takes place. The core produces all of the sun's energy. And we'll talk about that not today. The energy has to get out of the sun, though, and the energy is created in the form of radiation in the core. It has to work its way out. And so it leaves and it goes through the radiative zone. And that's the region that we would call the mantle if it was a planet. And so energy moves through the radiative zone by radiation. The heat has to get out somehow. And finally, the outer layer is the convective zone. And we've already talked a little bit about how convection works. When something is heated on the bottom, so for example, if you take a pan of water and heat the bottom of it, the warm water will rise and bring heat to the top. And there'll be a circulation like that. And that's what happens in the convective zone of the sun. Hot air rising from a sun-warmed ground. The convective zone is heated from below, and the heat's carried upward just by the material. And so those are the sun's layers. The sun's atmosphere has three layers. From the bottom up there, the photosphere, the chromosphere, and the corona, which we mentioned earlier. The photosphere is the lowest layer. It's the yellow face of the sun that children draw. The photosphere is a few hundred miles thick and has a temperature of about 10,000 degrees Fahrenheit, or 5,800 Kelvin. Its density is about 1/10,000th the density of the Earth's atmosphere. So it's really diffuse. It's super hot, and it's really diffuse. The chromosphere is the middle layer. It's about 1,000 miles thick. It sits on top of the photosphere. Its temperature is roughly 10,000 at the bottom, same temperature of the photosphere, and then 20,000 at the top. So it's getting hotter as you go up. Its density decreases steadily as you go up to about 10 million times smaller than the photosphere's density. And so the photosphere was 1/10,000th of the Earth's, and so you get the picture as you go up. Finally, there's the corona. Those were the rays of light that people draw, that children draw when they draw the sun. That's what the corona kind of is. The corona extends for millions of miles above the sun's surface. Remember, the sun's only 1 million miles in diameter, so it extends way up. The corona is about 1,000 times less dense than the top of the chromosphere, and so, or 10 billion times less dense than the photosphere. So it's just it's extremely diffuse. It's practically vacuum. Um, the corona has temperatures of about 4 million degrees Fahrenheit. It's super hot stuff that gets that. You have to have a huge amount of energy to get away from the sun's gravity. And so the stuff out there is very energetic. The density of the corona is so low that you cannot feel it, the heat if you stuck your hand, your arm into it. All you would feel was the vacuum. Even though it's 4 million degrees, there's not enough matter there to for you to feel it. The corona produces the solar wind. It's discovered by its effect on comet tails, which we already talked about. That's how the solar wind was discovered. The fact that all these comet tails have their tails, all these comets have their tails pointing away from the sun. The solar wind can be traveling up to 1 million miles an hour. Notice as you go up in the sun's atmosphere, the density decreases and the temperature increases. This photograph shows the photosphere. It's the thing you just take a picture of if you take a visible light picture of the sun. Also shown is a group of sunspots and the Earth for size comparison. Sunspots appear dark because they're a little cooler than their surroundings, but not a lot cooler. They're certainly like it. If the rest of the sun wasn't there for comparison, the sunspots would actually appear bright. It's just that the camera settings are set for the bright part of the sun. Not these images. These, for example, those dark spots would be much brighter than the full moon, for example. So the temperature of one of those sunspots is about 6,300 degrees Fahrenheit rather than 10,000 degrees Fahrenheit for the surrounding area. Just a little cooler. So these are granulation patterns on the photosphere. So if you zoom in on the photosphere, instead of seeing a smooth yellow surface that you might expect to see, you see these granules. And these are regions of just rising. It sits on top of the convection layer, and so there's regions of rising and sinking gas. And the bright part is where it's rising, and the dark edges is where the cooler materials are sinking. These granules, here's a sunspot, by the way. Remember we said that's as big as the Earth or something like that. These granules are maybe the size of a state in the United States, Texas or Missouri or something else. Just that gives you a feeling for the size of each of these. So they're enormous in size, at least compared to a human. They look really tiny in the picture. So the photosphere is the yellow circle we've seen photographs of the sun. A highly magnetized photograph will show that the photosphere is an extremely active layer. Granulation is hot gas rising. That's the bright centers of the gas, of the granules. And less hot gas sinking, that's the dark borders. Each granule is roughly the size of the United States. So again, here's sort of a composite image of the 3 layers of the sun. The chromosphere, which is the thing we get to see. Sorry, the photosphere, which is the thing that we get to see, has a sunspot on it. Here's the chromosphere, and here's the corona. The temperature, kind of hard to describe, but it kind of rises as you move out in the atmosphere. The horizontal axis here is how far away you are from the sun, from the core, say, or just moving away from the sun here. And the left axis is the temperature. All you need to know is that from the photosphere going outward, the temperature increases. Maybe not steadily, but it increases. This is a coronagraph. So they make these devices, and you'll see some pictures where the camera actually has a device in there that blocks out the sun so you can see the corona. It's really hard to see the corona in the sun if you have the sun in there as well. And so that's something that blocks out. And in this one, somebody has superimposed an image of the sun where the sun would be at the corresponding size. This is probably in the ultraviolet. Another picture that has coronal hole. You're sort of, the haze you're seeing around here is the corona, right? And this is a region with a hole. There's lots of weather, kind of stuff happening, variations in what's happening in the corona and the photosphere, all this stuff that's happening on the surface of the sun or in the atmosphere of the sun that we don't really get to see or think about very often. The largest sunspot shown here is 11 Earths wide. It's kind of amazing. This is just a detailed image of the sun. You can see the granules in here. These are sunspots. So sunspots are cooler spots on the photosphere. The sun has an 11-year sunspot cycle going from none, that should say none, to many, and then back to none. So one cycle, it goes from no sunspots to a whole lot of sunspots to no sunspots. That's how it works. Sunspots were first observed by Galileo and have been recorded ever since. At the very end of this section, I'll show you some charts. Many sunspots means the sun has greater solar energy output, which is a little weird if you think about the sunspots being cooler. But in fact, they correspond to actually a higher energy output because they involve flares and prominences and coronal discharge and stuff like that. And so the stuff that's coming out is actually more energetic when the sunspots are there. During the last half of the 17th century, there was a dearth of sunspots, very few sunspots over a period of about 70 years. Maybe from the middle 1600s to the early 1700s. It's called the Maunder minimum. During this time, Europe suffered some very cold winters. The sunspot cycle means if you don't have many sunspots, the sun is putting out less energy. There were other things happening on Earth at the time. There were some volcanic issues that were affecting the climate. And so, but climatologists are sort of looking at this now, trying to understand as they incorporate the sun's activity into the temperatures on the Earth. They're looking at these events in the past to try to see if they can understand the correlation between sunspots and Earth temperatures. These are already very carefully included in climate models. So it turns out that these sunspot cycles are correlated with magnetic fields on the sun, which is kind of interesting. In these pictures, these are called magnetograms, and in this picture, you can see just sort of white and dark areas. The dark areas where the magnetic field is pointing inward, so the North Pole points in, and the white areas is where it's pointing out. And so you can see all these little magnetic fields on the surface of the sun. The sunspot cycle is 11 years, but this is a 7.5-year set of pictures of magnetic fields on the sun. You can see we go from a lot to a little, and then increasing numbers again. And so the sunspot cycle, as it turned out, is correlated with magnetic field activity in the sun. So here's what happens. At the beginning of a sunspot cycle where you have no sunspots, or very few, the sun's magnetic field is very smooth. But the sun has this differential rotation where the equator rotates faster than the poles. And so the magnetic field, as time goes by, gets twisted up. And it creates loops and knots and stuff like this. And these loops and knots are where sunspots appear. They don't have to, but it's where they appear, when they do appear. At these sunspots, you can also get prominences and flares and coronal mass ejections, which we'll talk about. So this is a sequence of 4 images that shows the evolution over time of a giant eruption on the sun. Picture A is an event that began at the location of a sunspot. Picture B is a flare seen in the far ultraviolet. C is 14 hours later, you're getting a coronal mass ejection. I guess that's here, right? And then it's getting thrown out into the solar system here. So the white circle here is the size of the sun. So they've shrunk the sun down in these images so you can see what's leaving the sun. And so these things start at a sunspot, you get a big flare, and it gets blown out into space. Eventually, this stuff will reach the Earth. Again, it travels maybe 1,000,000 miles an hour. Um, and sometimes you'll see we have satellite issues because there was a coronal mass ejection, a CME, or they'll say it's going to happen in 2 weeks. So we monitor the sun, and sometimes we have to turn off our satellites so that when this matter comes through, nothing gets ruined. These are called plages. This is what happens inside the chromosphere. These little cloud-looking structures around sunspots. So various ways the solar cycle manifests itself. The number of sunspots increases during the solar cycle. We get flares, we get coronal mass ejections, we get prominences, and we get these plages. All of these are consequences, or things that are happening during the solar cycle. Here's another example. So this is from 1996 to 2006, and you can kind of see not very many sunspots, a whole lot of sunspots, not very many sunspots. So this is 400 years of sunspot observations, and this is kind of interesting. You can see that over the last 50 years we've had more sunspots in a while, although the last several sets of sunspots have been declining. And so, and the sun isn't nearly as steady as you might think it was. This is what I was talking about when I said the Maunder minimum. These are sunspots that, there were very few sunspots even at maximums of the sunspot cycle. And so the sun does things that we don't fully understand. But we've been counting these things heroically, I would argue. These have been counted by humans since Galileo started, since the early 1600s, and doing a more and more thorough job of it as we go. And so we're trying to, astronomers are trying to, and astrophysicists are trying to learn about the interior of the sun, the behavior of the sun, and how it affects these sunspots so they can know what's going on with the energy output of the sun. Here's some questions. Again, look at the PDF version of this document to get the most up-to-date questions.